Connected. And let's frame everything in here. What if I can get that on there? If I just stay on this side.
Your chance, do you have the papers you hand out on?
Oh, yeah.
Oh, hello.
Acids and bases. Okay, we're recording. Let me identify this thing. This is which one is this? And 5, right? No. Wrong chapter. Wrong chapter. EXAM8 chapter 16. And this is 16. Here we go. Okay. Let's see. Have I gotten your exam yet?
No, it wasn't on my blackboard.
It wasn't?
You had to scroll all the way to the bottom on the homepage. I'm just
On the homepage.
yeah, like you just click on this course and then scroll all the way to the bottom. That's what I'm talking about.
Underneath the other two.
Yeah, it's below the other test.
It wasn't on there. There was 5 and 6 that I didn't see the next one. I went to all the way to the bottom.
Okay. Don't let me forget, I'll check as soon as we finish today. All right. So let me pull out my review documents. See what we can do with acids and bases. That color. Okay. Anything in particular bothering you?
I just don't know.
Oh, you just got started. All right. Well, maybe we need to do just a little bit of review, just general review. Now, is this the class where we didn't finish, or did we finish in class? Sort of. And then I finished up and posted the whole thing. Okay, so it's all on Blackboard.
I need the review paper.
Oh, sure.
Oh, is that there?
You need the PowerPoint?
Yeah.
Okay. Questions on equilibrium. Understand what equilibrium means. Equilibrium is on the macro scale, what you can see, there appears to be no change. Right? But underneath, on the microscopic level, there's furious activity. For instance,
if you have a reaction like this, like that, these double arrows mean that the forward reaction and the reverse reaction are occurring at the same time. And the at equilibrium, the rate of each is balanced. Okay, that's why it appears that you've got so much here and so much here, and if you measure them now, measure them 10 minutes, and measure them 20 days from now, it appears as if there's the same amount of product and reactant. But actually underneath, the reactions are going like that and like that all the time. Okay. Now, if we need to express, and we can express this equilibrium in a formula, and it's equal to a constant value. You just take the products and multiply them together with their coefficients as powers. Okay. And then the reactants likewise. And that value, as long as the temperature is constant, if the temperature is constant, then that value will be constant. If you change the temperature, then this value shifts. But that's an equilibrium expression. And the reason I put that in the acid-base chapter is because we're not actually going to do the equilibrium chapter, but you need to know something about equilibrium to understand acids and bases. Okay. Now, when we apply this to an acid-base reaction, or when it simply to apply it to a, let's see, we'll use an example that we'll do that in just a second. I'll just make one up. Suppose we have an acid. How do we know that's an acid? There's a proton. That proton can dissociate. In other words, it can break into a positive and a negative. Cation and anion. That's an acid. It supplies protons. It's considered an acid. We react it with a base, sodium hydroxide. This too can break apart into the hydroxide and the sodium ion. And when they interact, it's just like a double replacement reaction. You just swap the cations. So the sodium swaps with the hydrogen and associates with chloride. This is all occurring in aqueous solution. And then the hydrogen ion associates with the hydroxyl and makes water. Okay? That's a typical acid-base reaction. Now, the interesting thing about, and we're going to be discussing acids and bases in aqueous solution only, right? Acid-base reaction can occur in non-aqueous solution, but that's not very useful in the life sciences. Everything happens in water. So the interesting thing about water is, whereas this is the acid here, this is the base, water can act like an acid or a base. In other words, in pure water, one molecule of water may act like acid, and another one would act like the base. That's called amphoterism. It can go either way. So if this is the acid and that's the base, that means this one has to give up a proton. And this one has to accept the proton. So if we do that, then we get, this one has lost a proton, right? And that positive charge goes with the proton to this group and becomes the hydronium ion. Okay, and that goes on in pure water. Now, sometimes you'll see this reaction written as just one water molecule. This is actually what happens. A proton never exists free in a solution. It's always associated with a water molecule or with some other molecule, okay? But for convenience, sometimes we just take one of these and dissociate them. So it'll look like this. Okay? That's sort of an abbreviated version of this. But I just want you to be aware of that fact. It means the same thing, only this is not reality. It's useful for calculations. Actually, that's not true either. Water is a liquid. Okay, the other thing about these expressions is there's a convention. When you write this expression, and let me see if I can think of one. I did one last week that had liquid, solid, and aqueous together. I wonder if it was part of the slides. So I could illustrate conventions. Gases. Those are all gases. Okay, so it's not behaving. All right. Well, I'll just state the rules then. When you write these expressions, if you see one of these after a compound or an element, it's excluded from the equilibrium expression. If you see one of these, it's excluded from the equilibrium expression. Solids and pure liquids never are part of an equilibrium expression. You will only have aqueous or gas. Those are included. So let's do let's talk about I want to get into acids and bases pretty quick because otherwise we'll eat up all our time just talking about equilibrium. Suppose, all right, here's the way we write a generic acid. You have the proton and then something else, okay? Now, in aqueous solution, right, that's going to be reactive with water. Transfer the proton to the water molecule and leave behind that anion. Okay? Now, convention. This is the acid. And it's the one that donates a proton. This is the base. It's the one that accepts the proton. That's the definition. This acid produces a conjugate base. Now, why don't we call it an acid? Because now it can only accept a proton. And only bases accept protons. Right? So this acid produces that conjugate base, and this base produces this conjugate acid. Okay? Now, the other rule you have to stick to is what is an acid conjugate base pair? What constitutes a pair? Well, obviously, you need this part of the molecule over here and this part over here. Right? So if you had something like this paired with that will work, right? Because this part mysteriously changed to that part, right? So the acid-base pair here would be that just lost a proton. And it can only lose one proton. If you have an acid that has more than one proton to give up, then the pair can only have lost one proton. Right? So if you write this one up here, then this one's going to lose one proton, and it's going to end up on the water molecule. Okay? So that's your acid, that's your conjugate base. Acid-base pair. If we had written that like this, that's not an acid-base pair because it's lost two protons. Those don't count. In acid-base reactions, we do one proton at a time. Okay? The reason for that is, it's a very solid reason, is that when you write the equilibrium expression for this reaction, take this one then, react with another water molecule, then you produce this plus that. The equilibrium for this one is very different than the equilibrium for this one. Now, it's possible, using Hess's law, to combine the two and get an equilibrium expression. But when you're talking about individual proton transfers, these two are very different from one another. Right? This proton, the first proton given up, is very easy. It comes off like nothing. So we call it a strong acid because it virtually gives up that proton, completely goes this way. But once you get to this negative ion and try to extract a positive charge from it, it's much more difficult because there's that attraction between the positive and the negative. So this one is a weak acid. It doesn't want to give up the proton. That one's a strong acid. Right? So only the first proton is strong, the second proton is weak. Let's see. So I sort of slid the strong, weak argument in there. Now, how about ways of expressing concentrations? You already know about molarity. So when you get, and by the way, when I was using, remember the square brackets, like that, that means equilibrium concentration. Can't use them until you get to equilibrium. So if you're going to talk about concentrations any other way, we use those. Right. That's equilibrium, that's not. Okay, when water dissociates, like I showed you before, this abbreviated version, like that. This is a pure liquid. These are aqueous. Okay? We can express these concentrations in terms of molarity, which is typical. So when that happens, pure water at 25 degrees centigrade, this concentration for hydrogen is going to be 1 times 10 to the minus 7. Okay? And since it came from this molecule, and these are 1-to-1 ratios, this one has to be the same. That's molar. Okay? Because when you dissociate this, you're going to get an equal amount of that on both sides. So this is what's called neutral. Pure water, just sitting there at 25 degrees, will have this concentration of hydrogen ions and hydroxyl ions. And they're equal. Whenever they're equal, you have a neutral solution. Okay? Okay, so the equilibrium expression for this equation, and we give it a special subscript for W, KW, for water, right? Very original. We would put this one at equilibrium over this one. And then typically what we would do is this one, like that. But the problem is, and the convention is, this is a pure liquid. Its concentration does not change significantly in this whole process. And since it doesn't change, we don't count it. Right? So the KW here is simply the expression of hydrogen ions and hydroxyl ions. Okay? So if we plug these numbers into it, 10 to the minus 7 times 10 to the minus 7 is what? 1 times 10 to the minus 14. Okay, at 25 degrees. That's the equilibrium constant for pure water. And this value has to be honored no matter what you do to that water. You add acid, you can add base. This has to be observed and obeyed. Right? So if we add some of this to keep that one constant, this one has to go down, doesn't it? Because products are always inverse relationships. So if this one goes down, that one goes up. If this one goes up, that one goes down. So if we added some acid to that solution and we say we got 10 to the minus 6 molar, right? That's an increase from 10 to the minus 7 to 10 to the minus 6. Actually 10 times. So what would this one have to be 10 to the minus 14? 10 to the minus 8. Okay. So if you know one in aqueous solution, you can find the other one. But there was a scientist by the name of Sorensen that just said, I don't like using all these big numbers. So he invented a logarithmic system to make it easier to manipulate the numbers. He called it the P system. And what he would do was, he would take the negative log, and he started with hydrogen ions. He would take the negative log of the hydrogen ion concentration and call it pH. Okay? So let's see what would happen. If we had neutral solution, 10 to the minus 7, right, for this one, then the log of 10 to the minus 7th is what? Minus 7. Because the definition of logarithms, well, in this case, base 10,
says that this value is the power of that number that equals this number, right? So the power of 10 to equal that number has to be minus 7. So this way, it would be minus 7. He didn't like minus numbers either, negative numbers. So he just stuck a negative in front, and that made it positive. Okay, so now he has a pH of 7 is neutral. So that means that in this case, a pH here would be 7, and a pOH, you can do the same thing. The negative log of hydroxyls is pOH. Okay? It's just a math manipulation. That's all it is. So you might have guessed, we could do it to that one too. Right? This value for KW, right? So we just take the negative log of this one, and that equals PKW. So the negative log of this is 14. The other way I show this sometimes is just say, all right, we're just going to go like this, take the negative log of the whole thing. Right? Negative log of that one, negative log of this one, plus the negative log of that. Or actually, the negative log of this one, the negative log of that one. When you take the log of a product, the log expression becomes addition. Remember? This is one of the rules of logarithms. The log of A times B equals the log of A plus the log of B. Right? So if we take the negative log of that, it'll just be whatever this happens to be, log of A, or negative log of A is PA plus PB. So if we do the same thing for this expression, it becomes PKW equals pH plus POH. Okay? And we know that PKW being a constant, KW is a constant, then PKW has to be a constant too. Right? So that expression is always equal to 14. Right? So if you know the pH, you can find the POH, just subtract it from 14. Right? That's a lot easier to manipulate than going through these powers of 10 and doing all that stuff. So if we know the pH is, let's say your stomach is behaving itself today and it's a pH of 2. That means that the POH would have to be 12. Okay? Let's see. There's another concept I wanted to introduce related to strong and weak acids. Am I erasing it too soon? Okay. Let's see if we can use some real numbers. All right, first concept. Strong acid. When we do this to it,
Actually, a strong acid is just that, right? You put that in solution, it all ends up over here. Whereas a weak acid actually, weak acid is like this, like that, mostly over here. So for this one, the K expression for the strong acid is huge. We don't even write it. It doesn't have any meaning. Because it's virtually concentration of that times that divided by this one, and if that one is 0 or pretty near 0, that's infinity, right? Anything divided by 0 is infinity. Okay. But this one does have value. So when we write the K for this one, and we use a subscript of A for K of an acid, equilibrium constant for an acid, then we have this one divided by, times that one divided by this one. Okay. So notice that if we have almost everything over here and very little over here, that expression is extremely small. Very, very small. Like, I don't know, 10 to the minus 20 or 10 to the minus 40. Some I've seen 10 to the minus 60. This is so small. But we can go on up and we can have a little bit more of this, and that increases this one and decreases that one. So then the constant is, minus 10 to the minus 7. That's not unheard of. But it's still a weak acid. Okay, so what do you get if this is your acid? Where's the conjugate base? I think. So think of what we mean by strength. A weak acid means that it does not want to give up its proton, right? So if it doesn't want to give up its proton, what if it starts over here? It has a strong attraction for protons because it wants to be here. So that means if this is weak, this is strong. Okay? Weak acids make strong bases. And the weaker the acid, the stronger the base. The stronger the conjugate base. Okay? So if we had a weak acid with a K, let's say the K for this one is like 10 to the minus 7. And we had another one where the K was 10 to the minus 25. Which one of those acids gives you the stronger base? This one. The weaker acid gives you the stronger base. Okay? Okay. The other concept has to do with what's the pH of that solution. Well, the pH requires that you know what this concentration is. That one right there. Okay? Then the question is, can the pH of a weak acid be be smaller than the pH of a strong acid?
Okay, think about what that means. Since based on the logarithmic scale that's applied to hydrogen ion concentrations when you make the conversion and the change in sign, the more hydrogen ion the higher the hydrogen ion concentration you have, the lower the pH number. If we run a scale, well, I'll do it down here. If we run a scale and we say pH gets bigger in that direction, this is neutral, right? And this is, well, let's just say, hold on a second. Let's do it this way. Let's do hydrogen ion concentration. It's increasing in that direction, right? So this is going to be acidic. That means this side is going to be basic. Because here, the concentrations are equal, 10 to the minus 7th each. Right? On this side, it goes 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, 3, 2, 1. So this would be 10 to the minus 6, 10 to the minus 7. Okay, and this would be 10 to the minus 2. Okay, on this side, the hydrogen ion concentration goes down. 10 to the minus 8, 9, 10, 11. Okay? So what happens to the pH? Well, what's the negative log of 10 to the minus 2? Just 2, right? How about 10 to the minus 6? It's 6. Neutral, 7. Over here, 11. So the more acidic, the smaller your number, the smaller the pH, okay? And for every pH unit, how much does the hydrogen ion concentration change? What's the factor? 10 times. Every time you change a pH, a whole pH unit, you get 10 times more or 10 times less, depending on which direction you're going. Now let's go back to the question. Can the pH of a weak acid be smaller than the pH of a strong acid? So in other words, if the pH is smaller, that means it has more hydrogen ion concentration, right? So is that possible? Can you have more hydrogen ions from a weak acid than from a strong acid? Pause to think. The answer is yes. Even though a strong acid is completely dissociated, if you start out with a low enough concentration and you have a high enough concentration of weak acid, it can, even though it dissociates less, it can produce more hydrogen ions than the strong acid. Okay? That's the difference between equilibrium constant and equilibrium position. Okay? Constant is constant, no matter what. So that value is going to be a certain number for the weak acid and non-existent for the strong acid because it's completely dissociated. But the equilibrium position can favor the weak acid in hydrogen ions simply based on its concentration and the effect of its K value. Okay? That's the point I wanted to make. Okay. We haven't even worked any problems yet. I just think we ought to do a few. Where are we in time? I always have to keep track of my time.
We got an hour now.
Yes.
Okay. So, the only thing we haven't talked about is buffers. And actually, in its simplest definition, a buffer, well, there are lots of different kinds of buffers, but for acids and bases, a buffer is a solution that changes only slightly in its pH if you add an acid or a base.
Like the bicarbonate buffer system.
Yes, for the blood.
Mm-hmm.
And let's see, what's its range? The ideal range is 6.35
35
to
7 point. No.
3.5 to 4.5, isn't it? It's pretty narrow.
Yeah, it's small. I can't remember if it's 6 point or 7 point. Sounds like, because it's I couldn't remember because on the test she had 6 point something something and then 7 point something something. And I was like, I don't know.
It's slightly basic. I think it is.
Because it's very controlled.
Yeah, 7.35 to 7.45.
Yeah, I think it's 7.35 to 7.45.
Yeah.
It's neutral.
And if you get outside that range, you start feeling it.
Oh yeah.
Yeah. So that is a very tightly controlled buffer system, and if you add acid to that, then it should compensate by stabilizing the pH within that range. So for a buffer, the pH won't change much. It's not constant. I mean, it's not held rigidly solid, but in a static system, which we're talking about chemistry here, then the pH will only change slightly. In an active system, like is in the human body, it will respond to compensate. It's not just buffer, it's an active buffer. So if you get a lot of acid in your system, in your blood, then it won't just sit there and take it. It will start pumping more carbonate in there to neutralize it. Right? Okay, so that's a buffer.
I think that's why a lot of doctors tell you not to do that keto diet. It puts all the ketones in your blood, and it'll cause your body to go into ketoacidosis.
Right, right. That's a danger for diabetics, particularly, because your body doesn't metabolize sugars very well.
Yeah.
So it goes to its secondary source, which are fatty acids. And they're really bad for producing acids and ketones. I remember one time I was watching this TV show way back, black and white days. And the star of the show was Danny Thomas. You ever heard of Danny Thomas?
What's he playing?
I think he's dead now. Maybe you know his daughter.
What did he play in?
He was mostly comedies.
I probably have seen it.
Heard of his daughter, Marlo Thomas? Okay. Anyway, he was playing the part of doctor in this show. And he had just moved into his new office. And there was no furniture. There was no equipment. And he had this guy show up at his door that was obviously in distress. So his receptionist, who was there helping him set things up, showed him into the office, and he had 2 boxes. So he sat the guy down on one box, and he sat on the other box. And he looked him over, and he leaned in, took a whiff. He says, "You go straight to the hospital right now." He smelled acetone on his breath. He was diabetic, and he was probably 400 or 500 by that time, at least, maybe more.
You can tell a lot, like through someone's mouth, the smell, and a lot of times if you have strep throat, it's gonna smell terrible.
Yeah.
What does the acetone, what does that smell like?
I can't describe it.
It's not.
It's not similar to anything.
You'll know if something's wrong because it's.
Stick around after class. I'll take you down to the lab and give you a whiff.
Okay.
And then you'll know. You'll never forget it.
Okay.
I used to,
I smelled it before on a patient.
yeah, I used to use it a lot in the lab. In fact, before you could get purified organic reagents in bottles, sometimes they call them spectra analyzed, we had to distill our own to purify it. And I would distill acetone in the lab. And the whole place was just filled up, even with a fume hood. The place would just fill up with the odor. I don't know how many brain cells I killed doing that. Okay, so let's work a few problems.
There's only 40 of them. 44.
Yeah, that's kind of restricted here. How about, let's just look at the first one, okay?
Do all the odd numbered ones.
Okay. So for one, the question is, how many moles of pure sodium hydroxide must be used to prepare 1 liter of solution that has a pH of 12.126? Okay, so what do we get? Well, we want a solution, right, of sodium hydroxide, and we want to know the molarity. Now, we want to know the moles, excuse me. Well, actually, the molarity. We want to know moles per liter. So that's molarity. How many moles of that to prepare a solution that is pH 12.26? All right. We can convert that to hydrogen ion concentration, but that doesn't tell us anything about this one. What we need is hydroxyl concentration, right? So why don't we convert this to POH first? So if we say POH is equal to 14 minus 12.26. Remember that relationship? Okay. So that would be, what? 1.74 is POH. And then we want to convert that to hydroxyl concentration. So by definition, this is negative log of hydroxyl concentration. Right? So in order to find this one, you take that negative over here first, and then you say this. Okay? This is, you need the anti-log of 1.74, negative 1.74. And on your calculator, it's 10 to the x power. Okay? Usually, there'll be a log button, LOG button, and then a shift key above it will give you 10 to the x. Most of them. The one I've got in my pocket now puts it on a separate key. I don't know why, they just want to be difficult to get.
Does it say log 10 on it? Is that what you mean?
LOG means log. LN is the natural log, so you don't want to use that one. Yes, that's log base 10. And the one right above it, there's your anti-log, 10 to the x.
I can't use this text.
Okay, so if we do this, what do we get? So I've got a calculator in my pocket. So 1.74, and I'll change my sign, and then I'll go 10 to the x, if I can find it. There it is. Yeah, so I get 0.018197 molar. Well, that's the answer, isn't it? Now round it off. So we rounded it off there. So that's how many moles of hydroxyl we need in 1 liter. And we can say that's also the number of moles of sodium hydroxide because this is a strong base, completely dissociates, plus it makes one hydroxyl for every one sodium hydroxide molecule. Okay? All right, that's number one. What are we going to do now? 3?
Which of the following is the strongest conjugate acid?
Is the strongest conjugate acid. Okay. Hold on a second. I don't know if there's enough information there. Let's see, how did I answer that? Oh, okay. This really takes some, I don't know if you've got enough background to do this one. We talked about,
I need to understand your explanation of it on this.
have we talked about electron affinity? We haven't. Okay, so that wouldn't be a fair question. Just ignore that one.
So X it out.
Yeah, X that one out. Or electronegativity.
I think that's our next. No, our next one's electrochemistry. Would it be with that? Chapter 18.
No. No. This is an introductory course, and somehow that question snuck in. Okay. So let's move on to something else. Well, let's look at 5. To see if you can calculate the pH of a solution if you're given the initial conditions of 111.9 grams of HCl, and we're going to dissolve that in 160 liters of water. All right? And we want to know the pH of the solution. So, to know the pH, we have to find the hydrogen ion concentration. Fortunately, dissolved in water, this is a strong acid, so it will dissociate completely. So all we need to know is how many moles of this are we putting in that. Right? So we can take this and convert it to moles, can't we? We just need to know the molar mass of hydrogen, which should be 3646. Right? 3545 plus 1.01.
Mm-hmm.
Okay, so we divide that, 111.9 by 3646. And I get 3.069 moles. And then our definition of molarity, moles per volume in liters. So we've got 3.069 moles and 160 liters. Gives me, and this is hydrogen ion concentration because there's only one hydrogen per, so this is also that, 0.01918 molar hydrogen ion concentration. And then calculate the pH. Let's see, log, and then negative.
1.7. Oh, round it off. 1.72 pH. Okay? So how do you work this problem? Like I say, I worked it forward. Look at the question. It's asking for pH. And to calculate the pH, you have to know hydrogen ion concentration. Right? So we need something that will give us the hydrogen ion concentration. We got the volume. We just need the moles. That's why I converted this to moles. Okay. Seven looks interesting. This is a concept question. We had the hydrogen ion concentration of a neutral solution at 25 degrees centigrade. Equals 1 times 10 to the 7. But if you increase the temperature, it's going to cause more water to dissociate. Right? It's going to make this happen. And it's going to drive it more that direction. It's going to make more hydrogen ions. But notice when it makes those more hydrogen ions, what else does it make? It makes more hydroxyls. So even at higher temperature, it's still neutral because we're making the same amount of each one. So with that being said, number 7 says, as water is heated, its hydrogen ions increase. That's given. This means what? A, the water is still neutral. That's true, because you're making the same amount of hydroxyls as you make hydrogens. So B, hydrogen ions are greater than hydroxyls, or C, hydroxyls greater than hydrogen. Those are both false. All right, B and C. How about D? D says hydroxyls also increase. That's true. So both A and D are true.
Can we do number 8?
Okay. Just this once. We're supposed to be doing odds. Number 8. Identify the Bronsted acids and bases. Oh, I didn't talk about that to you guys. Bronsted-Lowry bases and acids and bases are based upon what happens to the proton. Acids are proton donors. Bases are proton acceptors. And it doesn't even consider hydroxyls. It just turns out that hydroxyls are good proton acceptors, so they're bases. Okay, let's see. Oh, okay, so here's the reaction. HSO3 minus and CN minus HCN and SO3 2 minus. Now this is all in aqueous solution. Right, we just didn't write it in. So what's happening? Which one on this side is the acid? Well, you look to the other side and see which one's missing the proton. That one's missing the proton, so they had to come from here. That makes this the acid. And if that's the acid, this one has to be the base.
So on the other side, this one is the conjugate acid. Because that's the base, this has to be the acid. Because this is the acid, this one is the conjugate base. Okay, so that means it's AB, AB. Yeah. Okay. Okay, let's go on to 9. Which of the following is a conjugate acid-base pair? How about A, HPO4, 2 minus, and PO4, 3 minus. Acid-base pair. Is that true? Well, notice we've lost 1 proton from here to here. And this part stays the same. That's an acid-base pair. Well, based on the way this question is structured, that's it. You got the answer. The B is HNO3 minus. That's not even a. B is wrong because those compounds don't exist. C, how's C? Well, NH4 doesn't exist. I don't know, you may not know that. H2F, that doesn't exist either. The rest of them are just stupid. A is the only possibility. I'm glad I didn't write that question. There's some chemistry moron wrote that one. Let's see. See if we can find some that's a little different. Oh, how about 13? Which has the higher hydrogen ion concentration? 0.4 molar rubidium hydroxide. Let's see if that was right. Yep, rubidium is from the first column, so it's a +1. OH is a -1, so that's written correctly. And the other one is 0.2 molar calcium hydroxide. Calcium is an alkaline earth, so it's 2+, and it needs 2 hydroxyls. So, what do we need to know to answer the question pH? pH is equal, or greater than, or less than, one or the other. Well, if we find out how much hydroxyl this one produces and how much hydroxyl this one produces, then we can infer the hydrogen ion concentration, right, based on their stoichiometry, right? So what's the hydroxyl concentration? It only makes 1 hydroxyl for every molecule, so its concentration is this. How about this one? Well, that's the concentration of the molecule, but it makes 2 hydroxyls for every 1. So its concentration is the same. If they've got equal hydroxyl concentrations, they must have an equal hydrogen ion concentration. So this is the one. They have equal pHs. Let's see. The hydrogen ions are equal D.
The answer doesn't depend on the volumes. This is an intensity factor, concentration. Doesn't matter how much volume you have. You're still going to have the same concentration. Okay, questions? I thought that was going to be harder. How about 14? Just to see if that point stuck with you. Say you have a pH of 3 and a pH of 5. So which one's got more hydrogen ions? Which solution has more hydrogen ions, first of all? That one, right? Then the question is, how much more? How many times more hydrogen ion concentration is it? What's the difference here? A difference of 2 pH units, right? Right? 1 pH unit is 10 times. 2 pH units would be what? Right. 100.
Oh, 10 times 10.
Yeah.
Okay.
Right? So here's a quick way to fix that. The difference between these is 2, 10 squared. If the difference is 3, 10 cubed. The difference is 4, 10 to the 4th power. Okay? Because each time you change a pH, you go up 10 units. So I went up 10 from there. Then another unit, I went up 10 from where I was here, which is 10 more than that one. So 10, 10, 10. Okay. I'll let you guys pick one.
Okay, well, go number 15.
15? Okay. Calculate the pH of an acid solution containing 0.044 molar HNO3. If we want to know the pH, we have to know that. And luckily, nitric acid is a strong acid. In fact, I didn't list the strong acid there. Typical strong acids, hydrochloric, nitric, sulfuric, ClO4, perchloric acid, a very strong acid. It's not just strong. It's not just a strong acid, it's a strong oxidizer too. I used to use it to digest plant material. You have to take special precautions. If you want to see a real big light show, take a tall beaker with that much concentrated perchloric acid, and then take a chunk of butter about that big, throw it in there, put it on your hot plate, turn the hot plate on high, and pull the sash down on your fume hood, and then evacuate the building, because it will blow. So what we would do is we would take our plant material and put nitric acid on it, cold, and just sit overnight, do a pre-digestion. Then the next day we would add our perchloric and heat it up, no problem. Okay, so back to this one. So what is the hydrogen ion concentration?
right there, because it's one of these for every molecule. That means this is also the hydrogen ion concentration.
So we're going to have a calculator that can do that, right?
Yep. Sure do. So this should be 1.36. Now, can you ask yourself this question? Can you have a negative pH? Is there anything preventing you from calculating a negative pH? No. It's just math. Right? You could end up with a negative number. How about this one? If you have 4.9 molar perchloric acid, what's the pH? Well, it's 1 to 1, one of these for every molecule, so that's also the value, negative log 4.9 molar. Right? If we do our calculation correctly, the pH is minus 0.69. Now, while that's mathematically possible, it's not very useful. We typically don't deal with pHs that are outside the range of, say, 1 up to 12.5, or even less. The thing about it is, once you get to those extremes, it's difficult to measure. We use a thing called a pH meter. A pH meter has a specially designed probe that you put in your solution. It has a membrane on it that is differentially responsive to hydrogen ion concentration. Right? And when it allows that charge difference to occur on the membrane, it invokes a charge inside the electrode, and the electronics of the instrument pick that up. And they interpret that as pH. So if you've got extremes, then that delicate membrane doesn't respond as well. You need a specially designed pH probe to go to the extremes, very high pH, very low pH. And they exist, but most people don't need them.
How is that a negative and the other one is not?
Well, 4.9, take the log of it.
It's not giving me a negative on my phone. I was just wondering if I was missing a step.
Well, this part of the calculation right here is just 0.69.
Okay.
And then the negative gives you that.
Okay.
Right?
Okay, now on the one we did before that, how come that one was not negative?
Because this part of the answer was a negative number.
Oh.
Yeah. Yeah, a lot of students, when they first see that one, they do a Beetlejuice. Spin the heads around.
I think I got it now.
Hey, check my answer. Yeah. Let's see if there's anything lurking toward the end I don't want to miss. Oh,
the most common way to make a buffered solution is to combine the weak acid, let's use acetic acid. Okay, there's your acetate polyatomic ion. There's the proton that dissociates. And notice we've got more than one type of proton in here. These three are locked in place. They're not going anywhere. But this one is free to dissociate, although it's weak. And what it will do is produce this and this in aqueous solution. Okay, so a buffered solution is a combination of the weak acid and its conjugate base. So in a buffered solution, we're going to have some of this and some of that. And in fact, I don't have time to explain it now, but in fact, the ideal, there's a range of pHs, concentrations of this and that give you the best buffer zone, okay? And the best buffer zone is where the concentration of this at equilibrium is equal to that. Okay? So the ratio is 1 to 1. If those two are equal, you're right dead center in the buffer zone. Okay, so what happens when we add acid? I don't even know if this is part of the discussion, but it's interesting. If you have a buffer and you've got equal amounts of this one and this one, what happens when you add acid? Say we add more acid. What happens to that? Well, if this is a weak acid, what's this one? A strong base. It's going to latch onto any protons that show up in excess of the ones that are part of equilibrium, right? So it's going to attach to that, going to make that. So anything you add is consumed. In other words, no pH change. Okay? That's when you add acid. Now what happens when you add base? What happens when you add this one? Well, consider where that one came from. That one came from water. Right? Well, actually, it probably comes from something like sodium hydroxide, but we want to characterize it. This is a weak acid, right? It's also a weak base, but in this case, it's a weak acid. Produces a very strong base, right? So if that's a strong base, and we add that strong base, what's it going to do? It's immediately going to consume hydrogen ions, okay? That we would expect would produce a change in pH, right? It would decrease the hydrogen ion concentration. But what happens to it though? This is an equilibrium. So if you remove that, the reaction is going to shift that direction because it has to be an equilibrium. We talked about Le Chatelier's principle. Okay, I was hoping I had mentioned it during the equilibrium discussion. But Le Chatelier just says, if you disturb a system at equilibrium, it's going to respond to mitigate that disturbance. So if we remove hydrogen ions here, it's going to shift that way to replace those. Okay, so that's what happens when you add base. It combines with that proton, and then
shifts that over here. So that consumes some of this, but it also reestablishes that equilibrium where you have the hydrogen ions in balance. So acid, base, doesn't matter which, you're still going to stabilize the pH. Now, is there a situation in which you can exceed the ability of your buffer to consume acids or bases that you add? Yeah. Right. It's called the buffer capacity, right? So how would you modify the buffer capacity? Make sure you have more of this and this. If you increase those in the same ratio, you're still in the buffer zone, but you've got more capacity, right? Because if you add acid, you got more of this, so it takes longer to consume it, takes more hydrogen to consume it, vice versa. Same thing. So the buffer capacity depends on the absolute concentration of each one. Now, as a practical matter, particularly in the life sciences, a lot of the investigations that occur in the life sciences require buffers. Right? You want to stabilize the pH because living cells, they don't like to mess with their pH as much. They have an ideal range. So buffers are very important in life science studies. Right? Microbiology, any of the physiological studies, you want to stabilize that pH. So you would think that once you find the correct buffer, that all you have to do is just jack up the concentrations, right? And you can stabilize that pH over a wide range of inputs. Problem is, cells don't like high concentrations of these things either, right? Because it's not pH anymore that's bothering them, it's ionic balance, right? You jack those up a lot, and you're going to get these ions here, and they start messing with membranes, right? And so you have to balance the two between the buffer and the sometimes we call it salt index, high salt content. Okay. So any others? How are we doing on time? 11?
26 minutes.
Got about 25 minutes?
Yeah.
Okay.
I just have another class.
Oh, you got to go to class. Okay. Well, let's see. We've just about hammered all the major ideas here. Oh, number 37. There's another oddball. Let me see. I hope you can X that one out. I'm going to look at the exam and see if that one snuck through. Or one like it anyway. Now, if it's a bonus question, I'll leave it alone. There we go. So far, so good. Maybe I spotted that one in some other line. least the questions I'm worried about are part of the bonus, so you don't have to worry about that. Take a wild guess and see if you get it.
See you on Thursday.
Okay. Any others?
Not a suggestion.
Well, if you feel comfortable, we can call it a day.
My wife wants to.
Do what?
I was buying another chicken, my wife said, "Kill."
You bought another chicken.
Yeah.
My neighbors have, they bought 15 chicks. They're hoping 2 were at least